Hello everyone. The topic is isomorphic bisection of cubic graphs. Introduction. Graph theory enjoys application to a wide range of disciplines because graphs are incredibly flexible mathematical structures capable of modeling very complex systems. The study of complicated networks motivates the following important questions. To what extent can a graph be decomposed into a simpler subgraphs? Spearheading this line of research is classic problem of a graph coloring, one of the oldest branch of the graph theory. When the coloring a graph and seeks to partition the vertices into a few independent set as possible. Indeed, the subgraph cannot get much similar than independent sets, but such ambitious goals can at a cost. Not only the determination of a graph chromatic numbers, a not ominously difficult problem, but even when declaring with sphere graph classes, one can require many colors. For instance, many D-regular graphs cannot be partitioned in much favor than the independent set. Often one does not want to have such a large number of parts, and so it is natural to ask what can be achieved with favor colors. An early result along this line was proved by Lawes, who proved that given a graph G of maximum degree D, some number of color D and a sequence d1, d2 up to so on dt with summation di is equals to d minus d plus 1. One can decolor the vertices of G such that color class index a subgraph with maximum degree dA. Let's see a theorem. The edge of any cubic graph can be two-colored such that each monochromatic compound is a part of length at most 5. One can also try to find the different structure in the partition that just finding a part forest with more compounds. One attractive conjecture of Warrant from 1987 asked, whatever we can color the edge of every cubic graph with an aberrant color of the edge so that a red and blue subgraph forms isomorphic linear forms. This is known as hold for particular classes of graph. It was proved from gear graph in the work of Biron, Font, Habibi, and Wormald, and for some further classes of cubic graphs by Fouquet, Van Heerfen, Wajda, etc. Given Wormald conjecture, it is the natural to ask for analogous when coloring vertices rather than edges. In this direction, the following sticking conjecture was made by Andrew in 1990s. Conjecture. The vertices of any cubic graph can be two-colored such that two-colored classes induce isomorphic subgraphs. This conjecture was first mentioned in picture print by Abris Georgiabar, who draw conjunction between Van Rode conjecture and a conjectures. They further obtained computational result verifying the conjecture for graphs on the most 32 vertices. Hence, any counterexample to conjecture must have at least 34 vertices. Observe that any minimal counterexample must be connected, as the components of a graph can be colored independently. In this paper, we essentially resolve this problem and prove that large connected cubic graphs satisfy Android conjectures. This shows that there can be a most finitely many minimal counter examples. Theorem. Every sufficient large connected cubic graph admits a two-vertex coloring whose color classes induce isomorphic subgraphs. The remainder of this paper is organized as follows. In section 2, we present the proof of theorem. Point 3. Proof uses probabilistic method together whether declared the coloring argument. In the process of recoloring, we use some gadgets which we call PT reducer. The extent of the structure is shown in the section 3. Finally, we make some concluding remark and discuss open problem in section 4. Proving the theorem. Given a large connected cubic graph, our goal is to color the vertices such that the color classes into isomorphic subgraphs, and we shall find this coloring in two stages. In the first, we take a semi-random vertices coloring and shows that this is very close to having the desired property. Then in the second stage, we make some determinant local recalling to balance the two subgraphs and ensure they are truly isomorphic. Construction of constructing PT reducer. To complete the proof of theorem 1.3, we need to prove proposition showing that we can find PD reducer in the local neighborhood of every vertex. We will first show a very simple construction that works in graphs of grid at least 7, thereby providing a short proof of conjectures for large cubic graph without short cycle. The proof in the general case is a little more involved, requiring analysis of a few different cases, and we can found in the section. For any desummation and any sufficient large cubic graph G, there is a red or blue coloring of vertices from which following holds. Each monochromatic compound is a part of length at most 5. For each 2 is greater than or equal to t, t is greater than or equal to 6. Under root log n, there are the sequence of vertices correcting the bisection. The coloring from proposition is close to begin the bisection we need, but the number of short paths, the red, in the section stage of our argument, we will make the local changes to coloring to correct the descriptor. We do this gadget we call PD reducer. These are flexible subgraphs in the sense that they admit two different coloring which have the same monogrammatic subgraph const except for a short part. By choosing and appropriate coloring them, we can adjust the value of RPT and BPT, making them equal. When doing so, through we do not need to take care that our changes do not leak out and affect subgraphs out elsewhere. Conclusion: in this paper, we have proven Andrew conjectures for all the large conjectured cubic graphs. While this only leaves a finite number of graphs to be checked, and there is room to optimize the constants in our proof, there will still to be too many cases to be handled computational. Hence, a complete resolution of conjectures will likely require some additional ideas. In this section, indicate some ways in which our proofs could be modified, which might help makes program toward the full conjecture. In this sense that they admit two different coloring which have the same monochromatic subgraph score except for short path. By choosing an appropriate coloring, then we adjust the values of this, and by doing this, when doing so too, we do need to take care our changes While this only leaves a plenty number of graphs to be checked, and there is a room to optimize the point. So hence a complete resolution of likely requires some adjusting ideas.